Thank you everybody for being there, and to the organizer also for inviting me to presenting you this joint work with Olivia Caramello. So where I will try to reconciliate those two notions you have heard of during the school and the conference of morphisms and comorphisms of site. So in general, Grothendieck topoi, when I will say topoi, I will mean Grothendieck topoi in this talk, are presented through sites, and geometric morphisms between them are presented through functors between sites. And there are two classes of functors that are known to induce geometric morphisms, namely morphisms of site that are defined by a cover preservation property, and comorphisms of site, which are dually presented by a cover reflection property. And so one could ask why such a dichotomy exists, why both are able to induce geometric morphism while having kind of dualistic properties. And also one could ask, is it possible to mix them all together into a single structure and to make them live in the same place in some sense? And this is what I will try to answer in two ways, because there are two solutions to answer to this problem. So one will be through the formalism of a double category, and the second answer will be through a straightened notion of continuous distributor. So, but first I will recall a bit about morphisms and comorphisms, and especially from a bit the formal point of view of extension and restriction functor, which will make everything more quite clear and suited for categorical manipulation, and which will make everything that I will present it almost trivial when you just write it properly. So, so sites are data of categories equipped with Grothendieck topologies, or in what we'll choose in this talk, more generally, what we call Grothendieck coverages, which are slightly more general. So, those, in each case, you can present Grothendieck coverages or topologies, either from the formalism of families, covering families, which are families of map over a fixed object, or through sieves, which are subobject of representable. And this is this formalism that I will prefer in this talk, because they will be easier to manipulate in a purely categorical way. So what are sieves? They are subobject. A sieve on an object C in a category C is a subobject of the representable at C, and this is equivalently a set of map with codomain C, which is closed by precomposition. And this closure property, as it suggests indeed, allow you to close any family of map with a common codomain by just adding formally all possible precomposite. And you will say that a sieve is below, or is included, is below another sieve if any arrow in this sieve factorizes through another arrow in the upper sieve, which exactly amounts to ask it to be inside it set theoretical. And now we define a Grothendieck coverage as the data for each object of a family or a set of sieves that will be declared covering and subject to the axiom that the maximal sieve at each object, the maximal sieve is in your family of covering sieve, and at each arrow, the pullback sieve of a covering sieve is covering, where the pullback sieve of a sieve is the set where the pullback of a sieve on the codomain of a map is the sieve on the domain of this map, made of all arrows whose composite with this map factorized through a map of your sieve on the codomain. And So this what we call quadratic coverages, and often people close it with the axiom or with an axiom of locality to get quadratic topologies. But in this talk, I won't consider them because in general, those data are sufficient to define site, and often site just mean a category with a quadratic coverage. And in this talk also, this site will be considered always as small generated, not necessarily small themselves, but generated by a small category. So when you have a functor between sites, you can ask either them to preserve sieves or to reflect covering sieve in a suited way. So the first condition of sieve preservation, when it is combined with a good notion of flatness, gives a notion of morphism of site, while the other one, the cover reflection, allows you to define a notion of comorphism of site. And both induce geometric morphism, let me explain you how it works, but with this formalism of extensions and restrictions. So if you have a functor between two categories, you have a triple of adjoint functor, which I will call left extension, restriction, and right extension, where the left and right extension send presheaf to their respectively left and right can extension along the opposite of your functor, while the restriction simply precompose any presheaf with your functor. The left and right extension are covariant in the functor along which you do your extension, while the restriction functor is contravariant in your functor. I mean along natural transformation. And now, from this, in particular, you have an abstract way to compute this left and right extension. So you can consider for a functor f the left and right nerve, the left nerve being just the left can extension of the Yoneda embedding of its domain along your functor f, while the right nerve, which I will denote this way, d of 1 to f, is simply the composite of the Yoneda embedding of the codomain along your functor. And those nerve functors give you formulas, abstract formulas for the left and right extension as well for the restriction functor. So you can express the restriction along f as the left can extension of the left nerve along the Yoneda embedding of the codomain, or, which is a formula that I will use later, as the left can extension of the Yoneda embedding of the domain along the right nerve. And dually, you have formula for the extensions, in particular for the left one, which I will use, which is that the left extension along f is the left can extension of the right nerve along the Yoneda embedding. And in particular, this formalism applied to sieves will be, in some sense, the common thread in this talk. So, so let's apply the construction to sieves in particular. I will do this because I will use this formalism to re-express a bit in an abstract way what it is to be cover preserving and cover reflecting. That's why I'm introducing all of this. So if you have a sieve on an object on C with some functor f going from C to D, then the left extension along f of a sieve S can be computed as with this Cohen formula, or if you don't like Cohen, think just a weighted colimit. And it returns, in fact, the set of all morphisms into the image of your object C, over which you took a sieve, containing all map into f of C that factorize through the image of a map in your sieve S. And dually, if you have a sieve on an object D in the codomain category, then you can consider its restriction, which is also given by this Cohen formula, because of the left-hand extension formula we gave for the restriction functor. And here it returns at an object, this stuff returns the set of all maps into D that goes from an object in the range of your functor, and the fact that factorize through your map in your sieve R. So that are the map in R whose domain is in the range of the functor. And in particular, you can ask what it is when D is itself in the range of the functor. And in this case, it gives you the set of all map from some f of C prime into f of C. But those maps may not arise from map in C, in your category C, but in the only as map between the images, which may not, if your functor f is not fully faithful, they may arise just in the codomain category. So this tells you that this restriction of a sieve is not itself a sieve because it's a subobject of the right nerve applied to f of C, which is not representable. But it is locally in some sense, in the sense that for any sieve, you will be able to compute its pullback along the universal map associated to the nerve, which simply locally send the offset in C to the corresponding offset between images in D. And this gives you a pre-image sieve over C. If you add a sieve R on f of C at the arrival, you can define this pre-image sieve f minus 1 of R above C. And this is the set of all maps above C whose image lands in R. So now, with this technology, I can express a bit more abstractly what is to be cover reflecting and preserving. So you say, in general, that a functor is cover preserving if when you have a sieve on an object in the domain category, and if you have a covering sieve, so for a functor between sites, if you take a covering sieve, then the sieve generated from the image of arrow in this sieve is generating. And it just say that the left extension of this sieve is covering for the topology on D. And when you combine it with a flatness, it gives you a nice notion of morphism of site. And in particular, also, it gives you a notion of continuousness when you will say that a functor from a site to topos is continuous when it is a morphism of site for the canonical topology on your topos. And in the following, I will denote as a site flat the two categories of site, morphism of site and transformation of site. Transformation of morphism of site. So you can induce geometric morphism in a very standard way from them by taking for a morphism of site the left-hand extension of its suffification along the suffified Yoneda embedding of its domain. And the resulting geometric morphism has as inverse image the composite of the inclusion of sheaf followed by the left extension along your functor followed by suffification. And this defines a pseudo-functor from the two categories of site and morphism of site into the two categories of rotating topology. Dually, if you have a comorphism of sites, dually, you can define the notion of comorphism of site, which is just, in fact, the condition of being cover reflective, as the condition that if you have a covering sieve on the image of some object, we just here beware that when I will speak of comorphism of site, I will choose a convention that for comorphism of site will go always in the reverse direction from some D to some C. You will, at the end, it will be clear why I make this choice. So you will say that a functor from a site to another site is cover reflecting, or is a comorphism of site, if when you have a covering sieve on an object f of d, then there is a covering sieve in your domain category whose image is contained in your sieve at the rival. And in fact, it just said that the restriction, the pre-image sieve of any sieve on the image is covering for the topology on D. So in the following, I will denote as site sharp the two categories of site, comorphism of site, and transformation between them. And so, as it is known, comorphism of site also induce geometric morphisms because any comorphism of site induce a continuous functor given by the schiffification of its left nerve, this way. And from this, you induce a geometric morphism whose inverse image part is the composite of the inclusion of sheaf, followed by the restriction along your comorphism of site, followed by schiffification. And this defines another pseudo-functor, but from the two categories of site and comorphism of site, and which is moreover secondly contravariant, that is a contravariant in two cells. So we have those two pseudo-functors from those two different possible categories of site into the two categories of rotating dictopole. And one may ask, so how do we mix this all together and to have a single category with both morphisms and comorphisms? Can we define nicely a functor from this into rotating dictopole? And the problem is that morphisms and comorphism of site are a bit reluctant to live all together because they do not compose with each other. Because if you compose a morphism with a comorphism of site or the other way around, you will lose both properties in general. So how do we do? And so what I will present you is that there are two possibilities. Either you find a nice two-dimensional structure on site in which you do not require morphisms and comorphisms to compose, which will be the point with introducing a double category of site, morphisms, and comorphisms. Or either you find a joint generalization of those two notions, in which the problem of composition again is solved just by a more relaxed notion of composition. And this will be the point of the second part of the talk, which will be about the notion of distributors between sites. So first, I will present you a proposal for a double category of site. So just let me recall you what's the double category. So it's the data of a class of object, a category of horizontal cells, and a category of vertical cells, which will be decorated by this nice stuff, and a class of what we will call double cell, which will be square of this form, intertwining two horizontal cells and two vertical cells this way. And on which you will enforce the following axiom. So first, that any object admits both an horizontal and a vertical identity. That horizontal arrow together with horizontal identities form an horizontal category, form a category, so in particular horizontal arrow compose between themselves, and form a category which we call the horizontal category of your double category. And the same for vertical arrow. You require that vertical arrow compose vertically, and with vertical unit define a category which we call the vertical category of your double category. You also acquire a good notion of pasting of a double cell either horizontally or vertically. And on this you enforce some very natural interchange and identity rules, which I will not detail because the coherence condition of double category are not the point of what I want to tell you. But what I will, because the point is not necessarily all the delicacies of this, those two-dimensional structure, but more the point that in double category, vertical arrows are not really required to compose with horizontal arrows. They are just put all together in this nice, arranged in this nice way, and you just have those purely formal composites that are not required to correspond with any actual composition in some real two category. So that's the point. You don't need actually to be able to compose the horizontal and vertical arrows. Moreover, you have a notion of a double functor, which is a notion of which is the data of a function between objects, and an horizontal and a vertical component that goes between the horizontal categories and the vertical categories, and which send any double cell to a double cell between intertwining correctly the vertical and horizontal component of your double functor. And you moreover require, of course, a coherence condition relative to pasting and identities. As I said, the point is that you don't have to compose your horizontal and vertical map. The main example of double categories is a double category dist of whose objects are categories, whose horizontal maps are functors, and whose vertical map are distributors, and whose double cell just are a nice notion of natural transformation between those. But in this talk, the kind of double category we will get are very different from this one, because they are more symmetrical. Another kind of double category which will be involved is the one of quintets. So if you have a two-category K, you can consider the double category of lax quintets, whose objects are just those of K, and in which you use all map of K either for horizontal and vertical cells, and in which your double cells just are lax squares. And you can do the same also for op-lax squares, and you just have a kind of transposition duality between those two constructions. So now, just let's do this with site. Let's define a double category of site, which we call site natural, on site. So by having as object site, a small generated site, as horizontal morphisms, morphism of sites, and as a vertical morphism, comorphism of sites, and as double cell, just a lax square of this form. That is, to cell going from the composite of a morphism followed by a comorphism toward the composite of a comorphism followed by a morphism. So, okay, seems natural. So now, let's define a double functor from these two topoi. What do we want? We want a double functor whose horizontal component is the sheafification of morphisms of site, and whose vertical component is the sheafification of comorphisms, which I described earlier. And now we just have to understand how you manage two cells. And in fact, okay, there is just a very formal way to do so. If you have a square, a lax square of this form, of this shape, between functors, there is a canonical way to mix all together the extension and restriction. In fact, there is only one way to do so, which is D square, which will be a canonical two cell going from the composite of the restriction followed by the extension going in this direction, where you compose now this way, into the composite of the left extension followed by the restriction. You construct it just by mixing all together units, the naturality data of your restriction functor and the co-units for the... there is only one possible arrangement if you try to write it. And now let's apply this to sites. So if you have 4 sites and a 2 cell of this shape, so intertwining morphism of site horizontally and comorphisms of site horizontally, then you can use these two cell relating the adjoints, the extension and restriction, because recall that the restriction are what induce the inverse image part of the geometric morphisms from comorphism of site, and dually the left extension are what we induce geometric morphism from morphism of site. So we just have to shiftify properly this 2 cell by the topology on this site, the one which is in the right upper corner. And it will, if you shiftify it, you will get a 2 cell between the inverse image part of corresponding to the geometric morphisms induced respectively from the comorphisms of site and the morphism of site. Just it goes in another it goes in a crossed direction. And in terms of geometric, this will correspond to a 2 cell, a geometric transformation between geometric morphisms going in this direction. And in fact, this is just a double cell in the double category, the quintet double category of topoi and geometric morphisms with lax squares as a double cell. And this, okay, we have it. This defines a double functor from site natural lax into the quintet category of topoi, whose horizontal component is the shiftification of morphisms, and the vertical component is shiftification of comorphisms. Okay, and one perhaps you would be angry that I have you could say the same thing about oplax, where you use oplax cells as your double cell, and you could ask, okay, that's a pity that you have a new duplication of everything with now stuff that are the convention with lax and the convention with oplax, which works almost the same way. And okay, I think this can be fixed if you go a bit more general and define a double category of topoi with geometric morphism and whose double cell are natural relation. So we're using the fact that in topoi you have a nice calculus of relation to have 2 cells that won't be anymore biased in either one or the other direction. But I won't go in this direction now because I would prefer try to understand why we get a double category of site morphisms and comorphisms. And so there are, and because, so in particular, what is it an instance of a more general kind of a double category? And why is it a kind of different of the better known example like the relational double category with the profunctors and this kind of stuff? So the answer is that it is an instance of a construction which is the double category of coalgebra, lax morphisms and co-lax morphisms of coalgebra for some 2, not commonad exactly, but some 2 pointed on the functor. So let's see how it is. So when you have a co-pointed on the functor on the 2 category, I understand as if it was a commonad, but we need to be a bit more general. Let's say just a co-pointed on the functor on the 2 category, which is just an endofunctor equipped with a natural transformation, a strict natural transformation into the identity to functor. If you have this, you can define a coalgebra for such a co-pointed endofunctor, which is just a pair of an object of your 2 category together with a strict section of the co-unit. And you have also the pseudo version where you just ask a section which commute up which a section up to an invertible two-cell, but I won't care much about those strict mesh issues. And what you can define interestingly are the notion of lax and co-lax morphisms between coalgebra, which will be the data, which will be pair consisting of a morphism in your two category and together with a two-cell, so either in the lax direction or in the co-lax direction. So don't be mad at me if I changed my opinion about what is lax and co-lax. It's just a matter of convention, and here it will be more appropriate to have this convention. So it's two cells that intertwine your underlying morphism together with the coalgebra structure in this way, and which is subject to some coherence condition. So now, if you have a co-pointed endofunctor, there is a construction introduced by Grandis and Paré, so okay, for monads, but you can dualize and generalize to endofunctor. There is a construction of a double category of coalgebra, lax morphisms as horizontal cell, and a co-lax morphism as vertical cells, and with a lax square for double cell, where the lax square are just the only possible orientation of cells that is compatible with the morphism structure. And now, so you ask me, so let's try to construct a pointed endofunctor for which a site would be coalgebra, and the morphisms and comorphism of site would be respectively morphisms and lax morphism and co-lax morphisms of coalgebra. So when you have a category C, a coverage on C will be a choice of a set of sieves for each object, J of C, and in general it will always be closed, because if a sieve contains a covering sieve, it must be covering itself, so it will be closed, up-closed for the order between sieves, and it will in particular contain the maximal sieve, so by assumption of what are coverages. So in the following, I will speak of filters of sieve, which will be filtered in the poset of subobject. So in fact, we won't really, when I say filter, it's just not to say an upset, okay, because it's bad vibe, just to set, let's call it filters. In fact, when you have Grothendieck topologies, it will be also closed by intersection, but okay, it's not important here. Just understand a subset of the poset of a subobject of the representable that is closed, that is up-closed. This is what Grothendieck coverage consists in. For each object, such a filter. And if you have a morphism, the existence of the pullback functor, the condition that the pullback sieve of a covering sieve is covering, just say that will be a condition that your filter are correctly, that the pullback functor restrict between your filter. So you have a pullback functor between the poset of subobject between the domain and codomain of your map, and this pullback functor between the poset of subobject induce an inverse image functor between filters of sieves that send a filter of sieve to the filter whose pullback land in your filter. This defines a morphism between the poset of filter of subobject of representable. And now, so let's try to define a category. Let's try to define an endofunctor from these observations. So for each category, I will construct a category S of C, whose objects are pair consisting of an object of your category together with a filter in the poset of subobject of the representable at C. And a morphism between those pairs will be simply a morphism between the underlying object such that the corresponding pullback functor between the poset of sieve, the poset of subobjects of the representable, correctly restrict between the filters, which just say that the codomain filter is in the pre-image along the pullback functor of your filter. This category is fibered over C, and it has posetal fibers, because the fibers at C just is the set of all filters of C. Okay. So now, when you have a functor, let's try to make this construction functorial. So if you have a functor between two categories, you can, so as I said, you can consider a left extension of sieves, and in particular, when you have a filter of sieve, you can take the direct image of this filter along the left extension functor and try to generate a filter from this direct image, and this is what we call the direct image filter, which will consist of all sieves that contain a left extension of some sieve in your filter F. And you can make it also, you can make this construction functorial relatively to the categorical structure on S of C. And in particular, so you can define a functor S of F that sends a pair made of an object and a filter to the pair made of the image of this object along your functor together with the direct image of your distinguished filter. And so this defines an endofunctor on an endo2 functor on cat, which is pointed thanks to the fibration, this projection to C, and which is natural, which commutes strictly with the F and its image along S, so that you have really a nice co-pointed endofunctor, and moreover, in fact, this extends to legs, you can show. And now, in fact, you can trivially see that a co-algebra structure for this endofunctor just is a Grothendieck coverage, because what it is a section of this fibration P of C. And what it just take any object of C to a filter of sieves. And moreover, it take, when you have a morphism between two objects, the condition, the way we defined what were morphisms in S of C exactly tell you that your filter, the pullback functor between poset of subobject restrict correctly between the filters J of C that are chosen by your section, the section that define you a coalgebra structure. So in fact, it's exactly the same thing as a coverage. And then, in fact, lax morphisms of coalgebra exactly are cover-preserving functors. Why? If you have a lax morphism of coalgebra, it is a two-cell of this shape. And because the category S of D has posetal fibers, this just, in fact, so this is a morphism of the form F of C with the next extension of G of C to F of C, because this is how S of F is computed, to K of F of C. So it compares direct image of covering a sieve at the beginning with covering sieve on the image at the arrival, and requiring to have a lax morphism structure just is the same as requiring an inequality, an inclusion of sieve, sorry, an inclusion of filters, saying that the left extension of this filter, the direct image for the left extension of this filter J of C, is included in the filter K of f of C. And this exactly tell you that if a sieve contains the image of a G covering sieve on C, then it is K covering for f of C. And this exactly amounts for f to be cover preserving. And dually, if a functor bears the structure of collax morphisms between algebras over its domain and codomain, sorry, coalgebras, then it is a cover reflecting. In this case, so you have a two cell in the converse direction. We just express the reverse inequality that covering sieves over the image are in the direct image of covering sieve along the extension, but it just exactly say that any K covering sieve on f of C contains a sieve, because this is the way we constructed, we generated filters from the direct image, contain a sieve which is of the form lext f of S for some G covering sieve S on C. This is exactly what it means to be cover reflecting. So we are happy. We understand why there is a double categorical structure. It comes from something very natural. There are lax and oplax morphisms lax and collax morphism of coalgebra for something which perhaps is commonad. I don't know yet. Maybe. I would like to tell you soon more about that. In particular, I think we can express the locality condition of Grothendieck topologies relatively to this functor, but I still don't know exactly how, but probably there is more to say about that. Okay, I could tell you a bit more also about this double categorical thing, like what are the natural double categorical construction in this setting, like tabulators. There are, for instance, tabulators in this setting are exactly what you heard of in Olivia Caramello talk when she constructed a comorphism from a morphism of site by using the comma and so on, and using the Giro topology on it and so on. This is, for instance, just a tabulator construction in this context. There are also very strange conjoint cell that become companion double cell after shiftification. So there is a lot of double categorical phenomenology we could speak of, but I won't, because now I want to speak you to tell you something about distributors. So in this first solution, we mixed morphisms and comorphisms all together, so without actually really merging them. And now I would rather like to have a joint generalization of morphisms and comorphisms, in a way, in some sense that removes this, the orientation, the functorial orientation that are inherent to this notion, and resolves cover preservation and cover reflection into a more symmetric condition. And also, this will provide a nice way to fix a slight imperfection in the way, in the relation between morphism of site and geometric morphism, which is that if you fix two sites, then not all geometric morphisms between the induced shift topos are induced by morphism of site between those fixed sites. They are induced by a continuous functor from the domain site to the shift topos for the codomain site, but this does not necessarily restrict into a functor between sites. However, it restricts into a distributor. Now we could just ask, okay, what's the notion of continuity and flatness for distributor? So, so first, what are distributors? Because it's worth recalling this a bit. Even if you, those weeks, you had heard a lot of distributors recently. But so here it will be not in an enriched context. It will be just, okay, distributor of set. So it's just a distributor from C to D is just a functor from D up cross C to set. And it sends a pair of elements, DC, where I'll put a D on this side because I will express that there is a contravariance in D, in the same way that when you use a home functor, the contravariance is on the left and the covariance is on the right. So it sends a pair of elements DC to to set of what we would call heteromorphisms, because they are kind of a generalized morphisms going across category. And we'll denote them as those cute wavy arrows because like it crosses the sea between distant continents. You arrows in your domain and codomain categories act on those set of heteromorphisms just by pre and post composition. Morally, this is how you should understand it. And so there are a lot of distributors in life, and in particular, as you saw in Zerstube classes, for instance, any functor induces two distributors in a canonical way. So it induces first a right representable going in the same direction with this convention, which just corresponds to the right nerve I introduced at the beginning of the talk, and dually it induces a left representable going in the converse direction with the convention, and which corresponds to the left nerve. And okay, distributor composes with a coherent formula, so okay, nice. We have actually a big category of distributors. And distributors correspond, between the two categories, correspond with functors going into the pre-Schiff category, and also they are classified by pre-Schiff categories, and they correspond with the co-continuous functors between pre-Schiff categories, where you first send a distributor to the functor, which send a pre-Schiff to, which send an object to the pre-Schiff obtained by just fixing the object and letting the left contravariant component ranging over your codomain category D. And then the co-continuous functor between pre-Schiff categories is constructed by taking the left extension of this, will be called the left extension along your distributor, and is constructed as a left can extension of this pre-Schiff, of this functor going into pre-Schiff, along the Yoneda embedding. And it is computed through this coherent formula, which is very akin to the one we gave for left extension along functors. And it has also an adjoint, but I don't care much about this adjoint. What is interesting is that this construction interacts in a nice way with representables. So if you have a functor from C to D, so the right representable, the right representable distributor associated to F, which is in some sense the right nerve, has a left extension, the left extension along the right nerve. You have a compatibility between this notion, the notion of left extension for distributor, with the notion of left extension along F. But if you go the converse direction, if you have a functor from F to C and look at the left representable distributor, you have a twist, which makes that the left distributor, the left representable corresponds with the left nerve, and the distributor, the left extension of this distributor now coincide with the restriction along your functor F. So on the right, the left extension coincides, and on the left, the extension coincides with the restriction. And we will use this, the fact that both extension and restriction in some sense are represented by the same notion of extension for a distributor to jointly generalize cover preservation and cover reflection. So, but first just let's see what it means to be flat for a distributor. Yeah. So it was already investigated some time ago by Benabou. Okay, when you say that a functor is flat when it's at each object the comma category is co-filtered. And in fact, you can do exactly the same thing for a distributor by just taking the graph at a given object. This also behaves like the comma category under a fixed object, and it is the category of all heteromorphisms going from a fixed object on the left. That is in your codomain category. And you can ask this category to be filtered, co-filtered, which means that it is non-empty. And when you have two heteromorphisms going this way, you can find another one into a new object and a span in the domain category whose composite with this heteromorphism give you the two one you started with, and the same condition for equalization of parallel arrows. And Benabou proved that a distributor is flat in this sense if and only if the next extension functor is left exact, which exactly says that the associated pair of functor between the left extension with its restriction define a geometric morphism in the converse direction between the preshift topoi. And in fact, any geometric morphism between preshift topoi is induced by a flat distributor between C and D. And in fact, you just recover, you just construct such a distributor from a geometric morphism by being the distributor that send the pair DC to the evaluation at D of the presheaf returned by F at C. Yeah. And so this defines a pseudo-fully faithful pseudo-functor from the B category of flat, of categories and flat distributor between them into the two categories of Grothendieck topoi. And it is fully faithful because we have those equivalents of home categories. But now, so how do we mix this with the topology? So this is what I would add as a contribution. It's for topology, we would like to have something that works, a single definition that would work for morphisms and comorphisms. Because in distributors, there is a kind of symmetry which is restored as opposed to functors which are more oriented. And here we would like a single condition mixing cover preservation and cover reflection. So how do we do this? But let's first see what extension along distributor does to sieve. If you have two sides, and you take and a distributor from C to D, and if you take a sieve on some object C, the left extension, as we defined along your distributor, so is computed as this coend, and return a set not of arrows, but a set of heteromorphisms from object D to your fixed object C, which are the set of all heteromorphisms from D to C that arise from another heteromorphisms into the domain of an arrow in your sieve S. That are the ones that does not just randomly appear, but were created by the cover in some sense. And the problem is that with this definition, with this calculation, you get something which is not, again, a sieve, but rather a subobject of this presheaf, the associated presheaf, the presheaf associated to your functor at C, evaluated at C. So this is not a sieve. Okay, but locally, in fact, it is. Because what you can do is, you can take, so it's nevertheless, so it has a monomorphisms into this presheaf associated to the distributor at C. And when you take an heteromorphism A, it is a map, so by Uneda lemma, it is a map from the representable at D, the guy who is on the left of your heteromorphism, toward this presheaf, and you can take the pullback. And in fact, this pullback return you, by stability of monomorphisms, return you a subobject of the representable at D, which consists of all maps from an object over your D, whose composite with your heteromorphism, by the action of the distributor, itself factorized through a map in your sieve S, which is expressed by this kind of square. And this defines a sieve on D. And so you have a nice notion of, okay, the left extension are not sieve, but at each heteromorphism, this pullback extension, this object, this pullback is a sieve. So to define what it means, a good notion of, it allows you to define a good notion of continuity for distributor. So you would say that a distributor between sides is cover distributing if for any pair of objects, D, C, and any heteromorphism from D to C, and any covering sieve S on C, the pullback of the left of the extension of S along your distributor is K covering on D. And this notion, what is interesting with this notion is that it jointly generalizes cover preservation and cover reflection, in the sense that if you have two sides, and if you have a functor from C to D, then this functor is cover preserving if and only if the right representable distributor is cover distributing. And dually, if you have a functor in the opposite direction, from D to C, this functor will be cover reflecting if and only if the left representable is cover distributing. So we have, in each case, it gives you a distributor in the same direction with the same property. So for cover preservation, just you will use that, in this case, for the right nerve, you have a coincidence of the left extension in the sense of distributor with the left extension in the sense of functors. And you will use the fact also that covering sieve are pullback stable. So, and it's, when you write it, it's almost obvious, in fact, that cover distributivity for the representable is cover preservation. And dually, for cover reflection, you will have, building on the fact that in this case, the left nerve the extension of the left nerve coincide with the restriction. We'll have, when you look at it at an heteromorphism, locally, you get something, you get inequality between the pullback sieve and the pre-image sieve of some sieve. Using the fact that in this case, heteromorphisms are just arrows for the left, in the left case, arrows from D to F of C, and in the other case, arrow from some F of D to C. And writing stuff properly gives you exactly what you want. So now you can also mix a bit, you can mix those continuity conditions with flatness in order to get a good notion of flatness, flat morphism between sides. So it is very akin to the ordinary condition of flatness, but where you relativize stuff along covers. So I won't be into the detail because you don't have time, but it's very natural actually. And so you have a notion of a flat distributor between sites. And you will have that flat distributor that are cover distributing and use geometric morphism between the associated shift topoi. In fact, you can show that they are the same as what was defined in an old paper by Johnston and Grace as this equivalent as requiring that B-dense morphisms into a finite limit are sent by the associated functor, by the left extension functor, into a B-dense morphisms between the image by the left extension into the image of a finite limit, but okay, this is just another way to pack what we described. And in this case, you will have that not only distributors, continuous distributor and use geometric morphisms, but that you will have an adjunction for each pair of sites between geometric morphisms in the other direction between shift topoi and distributors, continuous distributors between the sites. And in this case, it is just an adjunction with this functor being faithful, because just with this definition, it may happen that two distributors induce the same geometric morphisms. Indeed, when the problem is that the shiftification for the topology on the codomain side may mix altogether distributors. But this can be fixed if you strengthen a bit your definition of what it means to be continuous by enforcing the condition that the associated functor of the functor associated to your distributor takes value not just in pre-shifts but in shift, which is exactly the continuity condition you put on morphism of site when you speak of continuous morphism of site. You require them to land in shifts rather than in pre-shifts. And if you enforce this condition, then this adjunction restricted to a proper equivalence, an equivalence of home category between the category of geometric morphism between shift topoi and continuous distributor between the corresponding site with this definition of continuous distributor. If you define this two-category seat trill with sort of site with continuous distributor and transformation, then you have a pseudo-functor, a contravariant pseudo-functor into top, which is pseudo-fully faithful, and composed with a left and a right representable construction, restrict to the ordinary shiftification functor for morphism of site and comorphism of site. And that's all, and thank you.